It's very interesting to be here every year from the beginning because the science doesn't change, it progresses, but what happens is the world situation changes, and I was very happy to hear the gentleman from Germany talking about renewables or so on and so forth. And since I was here the last time, it has changed quite a bit. And what I want to talk about is catalytic materials from theory to synthesis to commercialization, which is a difficult road, okay? And I have a special section here called Don't Waste the Waste, which I will explain when we get there a little bit later. Now, going back to sort of what a gentleman was saying in the beginning, in 2012, the Wall Street Journal had an article called the Gusher, the North American Gusher, and they were calling basically Canada, the U.S., Mexico, and into the Caribbean were producing so much that it was called the New Middle East, okay? And you can see on the right-hand side here is another thing from the Wall Street Journal recently showing the production of different shale liquids in the U.S. climbing. So we have this tremendous surge of hydrocarbons, okay? And that seems good. We also have a surging supply. This is another recent showing where the fuel increasing from Utica Shale across the United States. And again, the gentleman was talking about fracking or non-fracking. And what I want to say is somebody that used to be with Exxon used fracking for years. There was not a problem with it. So a lot of these things that we talk about, really what I want to emphasize is the science and not the politics. And one of the things that I really like to say is I heard somebody who you will recognize say, "Oh my goodness, the SUV in your backyard is more dangerous than ISIS." That was a recent quote because he was talking about global warming, which is going on in a meeting in France right now, and he was saying it's more dangerous than ISIS. Okay? And what I want to say about that, I don't want to carry on about global warming, but I, as a scientist, and I tell my students this all the time, if you want to talk about what's happening on the Earth with global warming, tell me first what the sun is doing. The sun over the year, and NASA has data, has been warming all the planets. And I always like to say, why is Mars getting warmer? Do the Martians have bigger SUVs? So all I want to do is emphasize the science, okay? And if you're going to bring up any of these various issues about whether we're going to use fracking or whether we're going to do renewable or so on, make sure that the basis is scientific. That's all I want to say. So recently, since last year when I was here, wherever we were last year, the prices have plunged. Okay, and this is just a chart here. I mean, you can all get copies of this and so on, but it's just showing you that there's diminishing returns, as it said, as the price has dropped. And that's causing a lot of concern in the industry, quite a bit of concern. But new opportunities arise. Okay, so that's what I want to talk about is the science behind the catalysts that the industry uses and some new opportunities that arise with low prices. Okay. Now this is an editorial that I just wrote for the Energy Quarterly, that's Materials Research Society, okay? And what it says is don't waste the waste. The picture up there is showing flares from petroleum wells. And I got interested in this when I read an article about NASA. It said there were 3,000 such flares over Siberia every night. And they were burning as much oil, you know, in the flares, energy in the flares, as the entire east coast of the United States used for transportation. So part of what we do there is don't waste the waste. There's so much energy, and so we have a program called, which is, we had underneath there shown patents that we have, okay? Process and compositions for methane reforming solarly. In other words, you can take CO2 and methane, reform it reform it with a solar light or solar collector, and you can make all sorts of good products, alcohols and things that you can sell. So instead of burning the methane and wasting the waste, make products use this process. Another one that we have here is landfills also are known to have flares and waste materials. We now know how to enhance the organisms that are under the ground to make more methane and then use the methane for energy. And there's a patent there that we have shown under there. So those are other opportunities. And one of the ones that interests me the most is that we're getting new materials from asphaltenes. Very interesting new materials, which is really the subject of another talk, okay? But there's a patent there. We have made photovoltaic devices out of asphaltenes and TiO2. So what I want to tell you is, even if the price is dropping, there's many new materials that can be made from the bottom of the barrel. And there's the editorial, which you can't really read there, but if you want it, you get it from the MRS, and I think it just appeared. Okay, now some of the other things that I want to talk about, which some of the people here have mentioned, is to turn the industry into green production and refining. We have all sorts of technology to clean up. There's a list there. Land farming, advanced bioremediation, because a lot of the refineries in the world are quite dirty. Over the years, they've created messes. I don't want to mention where the countries are. You know where they are, but there's some big messes out there that can be remediated. Solar distillation. Metals can be removed by a technique that we developed called phytoremediation, which means using plants. Plants can take the metals out of the earth, and then you collect the leaves. And one of the things that we always laugh about is phytomining. Why don't you put it in the field there where people are panning for gold? You get rich by taking the leaves filled with gold. I talked about the flared gas a little bit. And of course, we worked a lot on biofuels with algae. And I have stories about some of the refineries that can be converted into refuges for animals that are disappearing. And furthermore, and this is another talk too, we have some very interesting low temperature, low pressure ways of converting crude now. I call it grandmother's stew, where you just cook it at about 170 centigrade and put air through it and you get it upgraded. That's a different talk as well. Okay. Now, to start to talk about how you commercialize some science, I always show this to my students because I am a Gemini. So that means I'm two people. One of them is still at Exxon, and one of them is at the University of Texas, okay? And some of the references are there, too, because you can go all the way from theory. This is my approach, theory to synthesis to characterization and application, is what I believe is the real way we should be teaching students to go that whole route instead of being in individual things. And that, of course, includes chemical engineering in the application, okay? And one of the things I wanted to say here, too, is that theory and to synthesis to commercialization, it takes a lot of time, okay? And this is something that people don't normally appreciate. On the figure 1 there is an HDS activity of some of the catalysts that are named there, and Nebula, which is an unsupported cobalt moly catalyst, which is commercialized over the years, okay, by Albemarle. And the ones that we have now, which we call B1, are better than that in terms of performance in real feeds, and I'll talk more about that. But what I wanted to say there, the two gentlemen there, Stu Solid and Ken Riley, were Exxon, are still Exxon employees that worked when I was there. And Ken Riley on the right called me up last year and he said, well, I want to thank you for the science that you did at Exxon that made the commercialization of Nebula possible. I said, what do you mean? You're calling me now. That's like so many years ago. And he said, well, it took us 10 years to commercialize it, but it was based upon the science that you did. So the idea that when you want to commercialize something, catalyst or anything else, it often takes more time than people appreciate. And when I talk about the students, I tell them that too. And Porcel International is who is commercializing our catalyst currently. And I want to tell you that the drop in oil prices has affected them and all of the companies that want to commercialize things like catalysts. In the petroleum industry right now, they're scratching their heads and saying, I don't know if we can make any money for the moment. So that's another thing when you're trying to commercialize. You can do the science every day, but the commercialization, whether the company is going to make money or not, is a different issue. Now, when I talk about the science that was done back at Exxon, I want to acknowledge Dr. Lucchese, Peter Lucchese, who was a dear friend and the founder of Exxon Corporate Research Laboratory, who passed away just recently last year. I was very fortunate to be with him when he went, but it's a long story. He was a founder and a good friend, and he created the environment there that allowed theory, synthesis, commercialization, and all that. It was a wonderful laboratory and taught us all how to do that. So, Peter, this talk is for you. Okay. And let me just go back there that when Exxon takes the lead, there was a gentleman there, Sam Tauster. When I first went to Exxon, and we're talking about the 70s, okay, the automobile manufacturers were complaining because they were saying, Exxon's making bad gas, it's ruining our cars, and blah, blah, blah. You better make the gas better, and this had to do with the emissions and so on. And a gentleman named Sam Tauster, who was a scientist there, developed the catalysts that are in all of the cars today. These noble metal catalysts, I show you some data there. And Sam was the guy, he eventually went to UOP that did that. And that was my first experience as somebody that was commercializing, and he was a great, great scientist. And when we had parties at Exxon, back in the good old days, he used to play the piano. And those of you who have seen Casablanca, the movie, we used to say, play it again, Sam, play it again. But I want to recognize Sam Tauster as being somebody that showed me when I started how you do that. And the other one, of course, was John Sinfeld, who's passed by right now, and he was my mentor, and we call it Goldilocks of catalysts, because on this side it's too hot, and this side is too cold, and this side is too just right, like the Goldilocks porridge story over there. And he also won in '79 the President's National Medal of Science. I was there at Exxon, and he had to go to Washington and get advice. And he was the one that really sort of set me on a course of understanding the basics. So I thank you, John. And so when I went to work there, first we worked on lithium batteries. And my boss that was at Polytech, where I got my degree, he said, oh, you're going to go into Exxon, you're going to work on catalysts. I said, no, I'll never work on catalysts. We're working on new energy, batteries, okay? Didn't quite turn out that way because it turned out that the batteries that we were working on, lithium non-aqueous batteries, were explosive and dangerous. Exxon had a company in those days that was producing them. And the fellow that was developing that, Dr. Stan Whittingham, who is a member of the editorial board of the MRS right now and a good friend, was nominated for the Nobel Prize in Chemistry this year. He didn't get it. Maybe he'll get it next year. And those of us that worked for him and some of the groups were talking, well, wait a minute. We did all the work. How come he gets the prize? It's kind of a thing that happens all the time, kind of a joke, okay? But it began to work on, when we were making all of the transition metals, began to make the series, and there it is there. And we developed this periodic trends. And this was really looking at Sinfeld's work and saying, what happens if we use any of the sulfides shown up in the top there, which we made, and we use a model reaction the HDS of dibenzothiophenone, and we got the trends over there, the volcano plots. And those volcano plots for years have been the basis for understanding the hydrodesulfurization activity of the transition metal sulfides. And there's a lot of theory there. We understand why ruthenium is the best. Okay, we know about the 4 and 5d electrons, and I don't have time to go into that, but we've done that. There's a paper on the bottom. And the other thing I want to say there, I showed a chart there where we have a mixtures of cobalt sulfide and molybdenum sulfide. And back in those days, they used to say, symmetric synergy. Look, you take moly sulfide, this plot there is the activity versus the amount of cobalt, and you put cobalt on it, the activity goes up. What they didn't say then, too, was when you look at the plot on the right-hand side, when you take cobalt 9S8 and put moly sulfide, it also promotes. And that was one of those scientific facts that was ignored at the time. It works both ways. And what that did was, when you look at the volcano plot, and you look at where moly is and cobalt is, you begin to realize there's sort of an averaging of bond strength. And that's the basis for the promotion effect, the averaging of bond strength when you get the right interfaces. Okay? And so I'm saying a little bit more about that right here, where some of the gentlemen, like the Comos phase, Topso, and so on, were talking about how important it is to have the cobalt on the edge. And basically, they're ignoring the other side, the cobalt 9S8, which is promoted, and so on. And some of the people up there, Contact Synergy, this fellow Delmont, who was from France back then, was saying you have to have the two phases in contact. And when the two phases are in contact, which I'll show in a bit, that's how you get the promotion effect. So he was correct. And, again, I say to the students, when you get in trouble with the graybeards because you're not agreeing with them, make sure you keep your thoughts, of what you think is correct and pursue it. And so this is what we did a long time ago, where we said that when you have the interface, you're going to get a promotion, transfer of the d electrons. And so when you look at this there, when you put nickel there, you get 2 electrons, so it goes up. It has 4 electrons instead of 2 of the moly sulfide. It goes up, and when you put cobalt there, you get 1, and that makes it look like rhenium. And all of that was shown. We have never been able to make anything that has 6 like ruthenium up there. And the thing that was interesting about it was when you put the copper next to the moly sulfide, what it does is pull an electron out. So it poisons it. And that was unknown. And we made the measurement. The publication is down there, 1984, to predict the poisoning. And by the way, it was very interesting because there was theorists in the room that were saying, you use X alpha. That's an ancient, like using a Model T Ford in '84. And they were questioning me and saying, you're using the wrong theory. And I said, look, go and look at the data versus the theory, straight lines, beautiful data. And I always say, if you're going to use theory, make sure you compare directly with data. And you guys can go in the corner and argue about which theory is better. But here's the straight line. This is all an extended talk. I'm not showing the activity versus the calculated d electrons. Now, the other thing I want to talk about, too, and this is something that I think is very important, is that if you're going to talk about catalysts, talk about the stabilized state of the material. I've seen so many talks where people get up there and they say, this is this, and this is going here, and here's the vacancy, but they get the wrong material. And what I'm showing here is, and this was something that the old engineers told me, okay? Unsupported catalysts, when you put them in the feed, they line up. They get more active. When you're talking about a cobalt on aluminum, cobalt moly on alumina, they line out. They start off at a higher activity and they go down, okay? So that was something that said, to me at the time, you really have to sort of understand what's being stabilized. Whoops, wrong way. And the answer was provided by this gentleman who was looking at our sulfides, unsupported sulfides, okay? And the unsupported sulfides, we was looking at a carbon grid to show the HRTEM. It was eating the grid like Pac-Man. And the old engineers at Baton Rouge, the old-time refiners, talked about hard and soft carbon when they regenerated the catalyst and so on. And if you treated the catalyst, took the hard carbon off, you destroyed it, okay? What is the nature of the hard carbon? And we figured that out at the synchrotron. This is data that was taken called NextF and EELS and so on. Basically, it measures the chemistry of the carbon edge. And when you do it, it only gives information from the first 10 angstroms, the surface, because the electron can only escape from the first 10 angstroms. And what it tells you is that the layer on top of the sulfide, if you have a sphere, and I'm going to show you in a minute, it's molycarbide. And there was some MOS2 with DBT, which we put in, right against molycarbide. And so it was discovery that said that when you put that catalyst in there, the inside is the sulfide and the outside is the carbide. And that's what I mean by establishing the structure, okay? And we also know that when you include carbon in the catalytic state and stable state, you get different results from the X-ray, okay? And that's shown here on the left and the right here. Conventional catalyst precursor have sort of a peak, low peak here. And so when you put the carbon in, like in that case it's iron, you get a different X-ray. So the whole structure is changed subtly, okay? And what you want to do is you want to create the stable state in the highest surface area possible. That's the objective, okay? And so here's some of the ones we did that show that you have, surface pores like this, and you have all kinds of high surface areas. 300 is the top there, you can see that. And the pore distribution is very nice from an engineering point of view. You can control it by controlling the carbon precursor that leads to the carbidate phase. And this is something that we also worked out, which was argued, but today is accepted, is that when you use molysulfide, and shown on the left over here is the dibenzothiophenone pathway, the rim sites, which now Topsoe calls the brim sites, don't ask me why rim, is the one in which the aromatic can lay down and get hydrogenated. And the edge sites are one in which the molecule comes straight in and the sulfur gets removed without hydrogenating the aromatic rings, okay? And I was very interested because when I went, this is a commercialization issue, to a refinery in El Paso with some commercial manufacturers, the guys out there that were loading the reactors with the HDS catalyst were asking them, do you have more rims or edges? And I thought to myself, this science, which we did a long time ago, the guys in the field were now talking about rims and edges. And the reason for that is that this is how you control the hydrogenation capability of the catalyst. Okay. Now, finally, in this section, I want to not go through it, but we have proven that we have a structure like this over here. Here's the molysulfide, and here's the plane, the 111 of the cobalt. You split it, and you get this structure in here like this, which, when you get the interface, and we have what I've said before, which is important. We have all kinds of data that shows that this structure is correct. So we have real data. That when you have that interface, you get the promotion effect, and that's the way the catalysts are stabilized in the field. And there's another picture of it. the promotion interface. And what's very interesting about that is that when you get it, and again, all of this data which you can look at when you get copies of this shows that when we did HRTEMs and so on, that's what it is. Okay? And so this is my most recent student, and the idea there is what does the stack height do? If we have this interface, this is the promotion cluster. And the promotion cluster, if you look at it with the cobalt, moly, and sulfur, it looks just like nitrogenase. And a friend of mine who is no longer with me said, Russ, if you ever figure this out, it's going to look like this. And he had made clusters that looked like nitrogenase with cobalt and moly. And he was correct, Ed Stiefel. Okay? But the question then is, if we have the cobalt 9s8 and we start stacking it, what's better? So that's the what we are doing right now to optimize it. And these are some of the things here which show the science progress that we've had over the years. The last one, where we just have a couple of papers now, structure of promoted systems. Those are papers, you don't need to do it. But what I want to say now is that we have at least 3 companies who have tested these catalysts in real feeds, where we did this one was done in Israel. There's an alumina catalyst, okay? And you can notice that when this was done, these are our catalysts here, 2 to 2.8 times faster activity in the real feeds. Now, 2 to 8 times, that's almost 3 times, and that is consistent with the theory. And one of the guys said to me, well, you got 3 times as much metal in there, which is consistent with the theory. He says, I don't want to pay that much. I said, well, you can pay 3 times more for our catalyst, or you can build a new reactor. Take your choice. Okay. So we have lots of data like that. This is another real feed test, which was done by Oxford Corporation. Again, here is the residual sulfur with the standard KF767. This is what this catalyst did. Residual nitrogen, all better, and we consistently, by making these unsupported catalysts, have this type of data. And I also want to say in period of commercialization here is that what you need to do is you've got to have, and this is something I learned at Exxon, you must have intellectual property. And what I've shown here is you've got key patents, you're surrounded by a wall of some fringe patents, and you have some internal know-how. And it's kind of a sneaky strategy because some of the fringe patents are there to sort of confuse the enemy, okay, of what you're really doing. And these are the key patents inside, and then you have internal know-how, which you don't describe in the patents at all. And that's another key thing to commercialization, is to have an effective patent strategy. And I don't want to spend time on it, but we've got plenty of patents. You have to have the engineers react these things correctly. We always use autoclave for the DBT prediction. And if you want to do it correctly with the real feeds, you have to use a fixed bed situation, and you have to understand the relation between the two. The other problem in the scale-up is you have to stabilize the pellets, where we're using 2040 mesh things, and you have to be able to make it. So finally, this is the Porcel UTEP relation, looking for customers to commercialize, and we also work with Chevron. And the other thing I want to say, which is shown in this slide, that's a deep sea vent. Okay, and what it's doing is the Earth's crust is spitting out into the cold water 3,000 feet under the Baja, in this particular case, and the black powder there is iron sulfide. And I was invited several years ago to the Santa Fe Institute to talk about the origins of life, because the scientists there believed that this iron sulfide, 3,000 feet down, was creating the molecules that were necessary for the origins of life. And my introduction was, I don't know anything about the origin of life, but my life began on sulfides. And the way I want to talk about it is just to show you here, there's so many reactions that the sulfides do differently. Here's ruthenium sulfide with water and steam, and I think Exxon commercialized this. You get the oxygen to add to the olefin. If you just use ruthenium metal, you get CO2 and hydrogen, water. So there are so many reactions that it does, and it's right now one of the big things is CO hydrogen making alcohols, and we're working on that, and we hope to be working with Dow, and I will be talking about that back east in March. So finally, petroleum refining, tar sands upgrading, using the, say don't waste the waste. So thanks I know I crammed a lot in here, but thanks, and I'll be happy to answer some questions.